Oh. All right, everyone. Shall we get started? Looking a little thin right now. But it is time, I think. Let me just make sure. All right. Yes. It is definitely time for us to get started. So, final lecture before the midterm. Any questions, any thoughts on your minds before the midterm on Monday, which will be in class right here as we had originally planned. Yeah.
Is it going to start at 6 then or 6?
No, we'll start exactly at 6, so you get the full time. Yeah. Yeah. Yes.
Is it assumed that most people will finish it?
That's my hope. That's what I always hope every year. Sometimes my hope is correct. Sometimes it's not. So we're trying to design it that way, so that everyone can finish. Yeah. Sorry. And whatever you prefer. Yeah, we are completely agnostic to that. Just as long as it is scannable, you know. That's all that matters. Any other questions about the midterm? Yeah.
Is there a question you want us to ask you about the midterm?
No. I just want to know what, if you guys have any thoughts or concerns or anything like that. Yeah. Sometimes I get like student requests. There's still a little bit of time, you know, to implement them. But yeah, like I'm definitely very open to hearing your thoughts about it. Yeah.
Will you be able to ask questions during the exam?
Yeah, so it'll be during, like it'll be here, and I will be here unless something happens unforeseen. And absolutely, you can ask for clarifications. We do try to debug our exams, you know, as much as possible ahead of time, but sometimes there's some typos and things like that. So please, definitely, if you find something you're like, wait, can this really be true? Then definitely ask. Raise your hand and ask. Yeah. All right, I see some stragglers coming in. Yeah.
So the exams are
The exam will start at 6 sharp. And that is just because I want to give you guys as much time as possible. So we'll start at 6 sharp. I'll let you guys, you know, work until 8 if you need to, and then we'll finish the exam. So you get a full 2 hours. My hope is that you won't need the full 2 hours, but we do want to make sure we give you that. All right. Again, any other requests? Anything you'd like me to do or not do on the midterm? Yeah.
Like what? Like what in the past that people requested?
I mean, people had all sorts of requests, like the length of the midterm and things like that. There were years in the past where students wanted like some options, like whether they could answer question 1 or answer question 2. But the interesting thing was, whenever I did that, after the midterm, people didn't want to, like they were like, actually, we wish we hadn't asked for that. So I think we're just gonna not do that, unless someone has. Like, if you guys feel very strongly about it, we can still potentially mess with it. But yeah.
What's the best way we can ensure that we can get at least some partial credit, even if we don't get the full question credit?
Excellent question. Yeah. So I again want to always remind you that if you know that your solution idea does not work, right, then you should always begin your answer with, I know this doesn't work, but here are my thoughts. And then present your idea, and then tell me why you think it doesn't work. Like, tell us why you think it doesn't work. Whenever you do that, you will get more partial credit, right? Because one of the key things that I'm hoping all of you guys are learning in this class is just like learning to know when you're wrong, right? Learning to know like when your solution is not working, right? So that's one immediate thing I would tell you. You know, when in doubt, try to explain more intuition behind whatever you're doing. Again, just so that we want to give you as much partial credit as we can, but we have to see it, right? We have to see like the reasoning behind it. So if you are writing like really succinctly and you're like, here's my construction, it works, right? And then it's wrong, then it's really hard for us to give you partial credit for that. So please try to explain as much as you can. Yeah. Yes, there will be extra credit. What's that? That we haven't determined yet. But okay, so also just so you guys know, there will be extra credit, but when we give an extra credit problem on any exams, then we grade that much harsher. So it's like, it's harder. We don't give that much partial credit for like extra credit problems. Just keep that in mind. But there will be a healthy amount of extra credit. Yeah.
Like when you're answering like questions, like what would constitute like getting partial credit for something versus like something that wouldn't like receive partial credit?
Sure. So let's say that you're trying to construct some machine, right? So we give you some new kind of machine, you try to construct it. And you know, you miss some case, right? But you know, so then if you just missed the case, then we would take some amount of points off, but we would still give you as much credit as we can. If you miss the case and realize it and like, actually, I realize it doesn't work on this example, but it kind of works on everything else, then we'll give you even more partial credit. And then, of course, the most is if you just actually get it completely correct, right? Yeah. Yes?
Are you going to release a key for the practice?
Yes, yes. In fact, we will do that tonight. Does that sound reasonable for you guys? I want to make sure all of you guys have actually tried to do it, though. You know, we don't want to release the key too early. Would people like to have it tonight? Can you raise your hands if that's a good idea? Or tomorrow? Any votes for tomorrow? Okay, I guess tonight. All right, please release the key tonight. All right. Any other questions? All right, if there are no further questions, then let's get back into where we were last time, right? So we had just, excuse me, we had just pretty much like almost completely proved a context-free pumping lemma, right? And boy, what is this? Very strong smell. Excuse me. Right, so the context-free pumping lemma, actually, yeah, you know what? I don't like saying stuff. You guys tell me, what was the context-free pumping lemma? How do we say it? How does it start? Yeah? Yes. Right, so for all context-free languages, okay?
There exists
P in the natural numbers, right? Which we remember in terms of like our actual proof, we were thinking of this as being something like 3 to the v, right? I think that was what we had in mind. Okay, such that. What do you got for me? For all x in L, such that the length of x is strictly greater than p, right? Okay, and then what? There exists A, B, C, D, E, such that, what are the properties? Right, x equals A, B, C, D, E, so it's just a decomposition of x. And then for all k greater than or equal to 0, is in the language. Yep. Right. So we have this like symmetric pumping that is possible, right, where you can pump both B and D together. And then there was one more property that we proved. Right. This is just this like non-triviality property. Sorry. What did I do? Oh, it's over there. So the non-triviality property that we proved using that minimality trick, right, at the end, was that this is at least greater than 0, right? Excellent. Thank you. That was definitely worth a token. And there is, like, when we think about the analogy to the original pumping lemma, right, there was, like, one thing a little missing here, right? And one way to think about it is that if we want to apply the pumping lemma, right, to try to prove that some language is not context-free, then if you remember when we were applying the regular pumping lemma, then it was super helpful to be able to say, like, actually we can pump in the beginning of the string, right? Or we could say, like, in the first P characters, right? So we want to be able to say something like that because it's just really helpful when you're trying to apply it. Like right now, you know, if you give me some string, like the place where the pumping is happening is sort of completely arbitrary in the entire string, right? So this is the final, like the final boss, right, for proving the context-free pumping lemma. And let me just remind you guys what was going on. So we had our starting symbol, right? And because the length of the string was so long, right, we were able to conclude that there must exist some variable A that repeats, right? And like this was the decomposition. C, D, E, right? And yeah, and of course the way we got that B and D have to be like at least one of them has to be non-empty was by the minimality of this entire derivation tree, right? So this whole derivation tree. T is chosen to be minimal, right? And that immediately allowed us to conclude that both B and D can't be empty, because if they were, then you could just replace this larger subtree with this littler subtree, and that's equivalent, right? So that's where we were last time. That's what you guys had come up with, right? So what do you guys think? How can we get something here that would allow us to control at least some part of this? Like, can we say that AB is going to be small? Can we say that BC is going to be small? Can we say that CD? Can we say BCD? Can we, like, what? Is there some portion of this that we would somehow be able to control? And if so, how? Yeah.
So since like our pumping boundary is like B, C, D,
Mm-hmm.
can we just have a condition where the length of B, C, D is less than or equal to P, like from the
Okay. So you suggest that we focus on this, but why? Like what is it about BCD that?
Because like the pumping boundary happens on that area, like the changes only happen.
Right. But I guess what I'm asking is, why should it be that BCD will be small? Like, how can we hope to guarantee that? Like, maybe the entire string X is some insanely huge number, you know, like 2 to the P, some insane massive thing, right? So how can we actually make sure that BCD is going to be small? Do you have any thoughts about that? Like, why should that be? I like that you've zoomed us in on something, but why? Right? Like, how can we control anything here, right? It's not obvious right now. Yeah.
technically we keep pumping down on like BCD is actually the length of deeper is easier than 0 to 4 fold because at some point when we pump down enough, there won't be enough length to be.
So hold on a second. What you're saying is that if we were to pump down and we just keep pumping down, right? But observe, as soon as we pump down once, we've actually got a different string, right? Like we would have to go back to the pumping lemma and it might decompose it in a completely different way, right? So that's a good thought, right? But it doesn't quite work, right? Because we have to be able to say that for a given string, for a given x, right, without moving to some other string, that there has to be a way of controlling some substring in it, right? It's a valiant effort, but doesn't quite work, right? And this is something, like it's not that obvious. We really have to think about it in a sort of a fresh way. Yeah. Okay, interesting. Okay, so what she's suggesting is that how did we conclude that there must be a repeat here anyway? It was by the pigeonhole principle, right? We said that the depth has to be, right? We concluded that the depth is strictly greater than v. In other words, it's greater than or equal to v plus 1, right? And that means some variable must repeat along some root leaf path, right? And what that means is, let's just give this thing a name. Maybe we can call it, what's your favorite letter? S? Did you say S as in Sam? Oh, X, no, we already used X, because that's the name of our string. S is good, okay, all right, thank you. So what she's pointing out is that the distance between these two A's, right? Like this distance is less than or equal to S, right? That is indeed without loss of generality, right? Because if this distance was more than S, then you could actually find another pair for which the distance is smaller, right? So that's a really nice observation, really, really nice like starting point for where we can begin. It's not quite done yet. Definitely worth a token though, okay? So before you try to fix it, let me just ask, why isn't this sufficient? If all we know is that the distance between the two A's is at most S, like what could still go wrong? Yeah?
Because essentially right now we're looking at the difference between like the variables as opposed to the difference on the actual strings.
Right, good. Okay, so what you're saying is that this variable constructs this substring, right? The BCD substring. This variable constructs this C substring, right? And what she's pointed out is the distance between them cannot be too big, right? Which is a really nice observation, right? And now what I'm asking is, does that imply that BCD has to be small? Like, does that fact imply that BCD has to be small or not? I thought I saw a hand there, but yeah?
I didn't understand properly, but I guess you could just have a bunch of A's repeating and a bunch of B's and D's on each side, right? Like in our derivation tree, like just because less than or equal to this number S here, we could still create a really long string, though. We could just have a bunch of A's repeated up, have a bunch of B's and D's on each side. Is that possible?
Well, okay, so remember another thing we had already figured out from before is that the arity of our tree is at most 3, right? So the branching factor is at most 3, right? So yeah, so maybe I'll stick with you. So this A here, how big could BCD be? Like how big could this whole string be? No, if we know that the arity is at most 3. Not sure? Okay. Sorry, I'm just saying that we know that this like first repeated variable is up here somewhere, right? We know it's at most s from its second repetition of it, right? And now the question that we're trying to figure out, right, is like how can we bound things, right? So like how big could BCD be? Like do we have any way of bounding it? Do we have any way of thinking about it? Yeah, is that a hand?
Yeah, I guess you were already talking about like 3 to the s, because it's like the arity is 3.
Uh-huh.
And then the distance between them is s.
Okay.
So there's
Okay, so let's think about that. So you have 3 to the s. Oh, sorry, s is just a number. So 3 to the s. But that only gets you to here, right? 3 to the s is kind of like letting us know how many nodes there could be here, right? Like at this boundary. Do you agree? But we care about going all the way to the bottom, right? Yeah.
Clarification, we never bounded the depth, right? We just kind of say a string that's bigger.
All we know so far is that the depth is at least s, right? Like the distance, the longest distance between that, oh, I guess that's s. Anyway, the starting symbol, okay? The distance, the longest path from the starting symbol to the leaves is at least s.
So that means they could be B, C, and D could be whatever size.
But yeah, right? Like it's at least this much. So it could be like a billion s, right? In which case this is 3 to the billion like s in size, right? So far we haven't quite gotten where we want to go, right? But it's still a very nice observation that this must be at most s. Is there any way that we could bound like the actual height of A? This is what we actually care about, right? Like what is the depth of the subtree that starts at A? Can we bound that in some way? Yeah. Something like that. I mean, maybe. But sorry, what's your idea though? Okay. And what? But what? Like, remember, the length of BCD is just whatever comes from the upper A, right? Like whatever variable repeated, the one that was higher, like the shadow of that is what BCD are. Like we defined A, B, C, D, E this way, right? So what property of A could we use to bound BCD is the question we're asking, right? And what our current discussion has yielded is that what we actually care about is this, like, let's call it H of A, height of A, right? Or maybe, I don't know, A1. Like, I don't know, this is too, okay, sorry, give me a second. I realize this is confusing. Let me just call it H, okay? So H is the height of the upper A, right? If we can bound H, then we would be in business. You guys agree? Right? If we could somehow say that H can't be too much, then we would be good, right? So the question is, how can we do that? How can we argue something like that? Yeah?
Can we also bound at S? Because let's say A is like really high.
Okay, hold on. Let's just do that slowly. So you're saying claim H is at most V plus 1. Is that right? Okay. So what's your proof?
Well, you always have to keep within B plus 1. So you know, if it's more than B plus 1, you can always find another one. You know?
Exactly. Yeah. Okay, you're right. It's so simple I don't even need to write down the proof, right? This is actually just true for the same reason as what she said, right? Basically, instead of talking about the distance between the two A's, which is what came naturally to her while we were thinking about it, which is great, right? In fact, the same argument just works all the way down to the bottom, right? So we can actually just say that when you look at the height of the upper A, it must be below v plus 1 because if you just look from the bottom up, right, along the longest path, the longest root leaf path, look from the bottom up, v plus 1, you have to hit a repeat, right? So just let A be the repeat you get when you go from bottom up, right? Definitely worth a token. Does that make sense to everyone? Right? Just a different way of thinking about it. Yeah.
Why it's like v plus 1 and not 2. Like, why do we, yeah, like, why can't we say that the entire height?
Right. So we start from our leaf, which is a terminal, right? Then we go up. Every time we go up, we're only going to hit variables, right? Because the internal nodes can only be variables, right? So if we go up v plus 1 times, we must hit some variable twice by the pigeonhole principle, right? Because we've seen v plus 1 internal nodes, right? But they're only v variables. So at least some variable has to repeat. Does that make sense? Like earlier, we were looking at it like top down. We were saying, let's start at the root and go all the way down. Now we're looking at it bottom up. We're saying just look at some terminal, just keep going up. And as soon as we go up v plus 1 times, we must hit some variable that repeated itself. Right? Okay, excellent. Any other questions? Is that a hand? No? Okay. Excellent, right? So we get this. Okay, what does this imply? So if the height is at most v plus 1, what does that imply about BCD? Let me try to, someone I haven't taught. Yeah, back there.
If we have the branching factor,
Uh-huh.
then like the number of users
Yeah, 3 to the v plus 1, right? So the only annoying thing is that it's not p, right? P was 3 to the v. This is 3 to the v plus 1, right? So like one way of writing it is 3p, right? We could do that, right? That's one option. Thank you, definitely worth a token, right? That gets us almost to where we want. So let me just write it here. So we could say something like BCD is at most 3p. That's what we proved, right? Yeah. Okay. Yeah, right. But remember, it's up to us. Like we decided what p would be, right? And obviously the argument only works better when you make p bigger, right? Like we've only had arguments that work better when p is bigger. So let's just redefine it to be this, and then everything else is still true. And we have a nice looking context-free pumping lemma, right? So yeah, that works, definitely worth a token. Okay. And that gives us like the current, like a nice usable context-free pumping lemma. Okay. I do want to make a point that with the regular pumping lemma, well, you guys saw in your homework that it is possible to make that even stronger, right? We can do similar things for the context-free pumping lemma. In fact, even more. Like this is actually pretty far from a characterization of context-free languages, but it's already very useful. So because we want to sort of keep moving, we're just going to stop here. But I encourage all of you to just think about it. Think about how you could strengthen this even more. It is definitely possible, but it is non-trivial. Any Any other questions about this? This is, as far as I'm concerned, this is just the proof. We've now given all the arguments needed to prove the context-free pumping lemma, and this is how we're gonna call it. Everyone good? All right, excellent, excellent. So we have in our hands now a pumping lemma for context-free languages, for languages that are decidable by PDAs, right? The only thing that we don't have so far is an actual proof that any given language is not context-free, right? So let's do it finally. Let's actually keep proceeding on like the great train of this class, right? We keep trying to come up with more powerful but reasonable notions of computation and then trying to prove what they can't do, right? So you guys already suggested a particular language. We can change our minds though. Any ideas? What should we do? What's a good language for us to target? Yeah. Yeah, okay. This is like the classic, right? Where remember our intuition behind this was that if you tried to do it with a stack, by the time you have confirmed that you've seen exactly as many ones as you've seen zeros, you've lost your whole stack, right? You've finished popping the whole thing off, right? So you have no memory left over to help you with your twos, right? And the intuition is actually a little less clear, to be honest, for context-free grammars, right? But that guiding intuition will still allow us to get everything to work via the pumping lemma. Which remember, the pumping lemma is really that push-pop intuition, right? That there's going to be things on either side that we can push because that we can pump because they kind of in our heads sort of correspond to this is like pushing something, this is the popping something, right? So let's do that. Let's prove that this is not context-free. This is our theorem. And I will now no longer give out tokens for just saying suppose not. So let's start with that because we always start like that, right? And so we assume that L2 is context-free, right? For the sake of contradiction, okay? And now let's get to work, right? You guys are pros now at applying at least the regular pumping lemma. Let's just think about how we would now apply the context-free pumping lemma in that same like tennis match way, right? So like, you know, we now have a context-free language. For the sake of contradiction, we can toss it over to the context-free pumping lemma. It's happy, it catches it because there's a for all statement here, right? We satisfy the context-freeness, and now it responds, right? Yeah. Right. So by the context-free pumping lemma, there exists a p in the natural numbers. Good. And now what do we want to do next? Okay, so you got to come up with a concrete string. What is the string that you have in mind? $2p, okay. Okay. All right. You're like, I'm not sure if p will work, so I'm going to throw in a 2 just for safety. You feel like it'll be easier? Okay. All right. Sounds good. I'm happy with whatever you suggest. All right. So totally worth a token. You got us started. This is the one that we're going to go after, right? Excellent, right? So we've tossed over an x. The pumping lemma confirms indeed its length is at least p, so it's good to go. It now responds with a, b, c, d, e, right? So now again, just remember, just like with the regular pumping lemma, we have no control over a, b, c, d, e, right? So we have to be able to handle whatever the pumping lemma gives us, right? So pumping lemma provides A, B, C, D, E, such that x equals A, B, C, D, E, right? The length of BD is at least 1, and the length of BCD is at most P, right? So now we've got to do our case analysis, right? And what do you guys think? How should we split this up into cases, given the constraints that the context-free pumping lemma gives us? It's really only this, right? This is the only like useful constraint that we can use. Yeah.
Yeah, since we know that BCD is less than equal to P, we
Mhm.
say that either BCD is all one symbol or maybe we should include two symbols maybe.
Okay. Good. So what you're saying very succinctly, right, is that either BCD is entirely contained among the ones, right, or it contains like some well, 0 or more ones and some number of zeros, or 0 or more ones and some number of twos, right? Okay. These two I totally agree are going to be like symmetric, right? So you're saying that's where they're basically just two cases. Okay. So let's do case 1. That was where BCD is just equal to 1 to the t, right? Where t is greater than or equal to 1, right? So it just falls into that middle area. So do you want to show me how we're going to get a contradiction in that case?
Yeah, we can try to, we try to pump down on it.
Yeah, pump down, right? When in doubt, pump down, right? So let's pump down. Right? So when you pump down, we're getting rid of BD. So again, we can imply that BD, since BCD consists only of ones, BD also only consists of ones. Maybe we can call it U, where U is greater than or equal to 1, right? And when we pump down, we get ACE, which must equal 0 to the 2p, 1 to the 2p minus u, right? Because we got rid of the BD part. And then 2 to the 2p. And that's a contradiction, right? This is obviously not in L2, right? So excellent. You got token for that. And then that's a question or an idea?
I have a clarifying question.
Yeah.
So why are we only doing this for just the middle part 1? Like, is it not possible the partition is turning into like?
Well, he suggested it. You guys are solving this, right? It's not me. So you guys suggested it, and that's how, yeah.
For 0 and 2 as well, because you could fit all of BCD into just the 0, and then have let E be the rest of the string, and like A is epsilon or something, right? So I guess we could like say without extra generality at the beginning.
Well, you know what? Whatever you guys suggest is what we're doing, right? So we already did this case, right? So maybe you can help me with case 2? So I'm still sticking with his overall like agenda, right? So the overall agenda was that case 2 would be that you have 0 or more ones, but at least 1 0, right? So that would mean that BCD is equal to 0 to the t, let's say, and 1 to the, oh boy, r, okay? Where t is at least 1, right? Because we definitely got at least 1 0. But r could be 0, right? You agree? Okay. Now, what does this imply about BD? Well, okay. The way that he suggested it, right, is very interesting, okay? And I would ask you guys to think, if we know that BCD contains at least 1 0 and maybe some ones, right? Then what does that imply about, let's say, or about specifically about BD. Like what is that?
Zero or one, like B must be zero.
Actually, this is kind of annoying. So, okay, that's a very natural idea. And by the way, I have to just like tell you guys, unfortunately, the context-free pumping lemma is just a little more annoying. Okay, the regular pumping lemma is so nice, so simple, easy to use. Context-free pumping lemma is a little more annoying. Okay, and what you're saying is actually very natural, right? You are saying, well, this better include at least 1 0, right? Because of the B part is what you were thinking, right? But annoyingly, we don't actually know that, right? Because this condition says that, you know, this is greater than or equal to 1, or D is greater than or equal to 1, right? Like one of them is actually allowed to be 0. So in fact, it could be that all the zeros are actually in C, right? It's still fine. Everything's still going to work out. It's just a little annoying, okay? That's all that happens. Yeah.
Wait, I was gonna ask, yeah, at this point, wouldn't it just be easier to just not use the pumping lemma and just kind of like create a string that follows the same conditions of the pumping lemma? It would be like the same thing, but you only have to give one example instead of showing an arbitrary example. I mean, just
I'm not aware of any trick like that. Like, the pumping lemma, as annoying as it is still honestly one of the simplest pumping lemmas that you could prove about context-free language, which is why, like, you know, you guys came up with it, right? It is like one of the simplest things you could do. And it's just annoying because we don't have any control over what the context-free pumping lemma will give us. So we're kind of forced to do some case analysis, right? But I actually want you guys, rather than rethinking the case analysis, to really feel wedded to his original idea, okay? Just because I want you to feel how you can like power your way through these things, okay? Because that is an important like skill to pick up, right? And I promise you this, the way that he's doing it is totally valid. This is gonna work, okay? I promise you it's gonna work. We just have to think about it a little bit slowly, a little bit like one step at a time, all right, to get it done. Is that a hand? Did you have a hand in the air? Yeah? Do you want to continue? So what is that? Yeah.
Do you split case 2 into 2 more cases? Or like, either B is empty or D is empty, and then if D is empty, then it's just the first case that we just proved, and if B is empty, then you prove that there's a 0 there.
Okay. Yeah. That is a valid thing we can do, right? I like the way you're thinking because underneath it is like this confidence, right? That things are going to work out, right? I'm still going to push back just a little bit because I want to show you, in fact, they'll end up being the same case, okay? So BD, let's just say, let me just write it this way. Suppose it's equal to U to the V, 0 to the U, 1 to the V, okay? So it's almost what you were saying. I'm just going to slightly modify it just to sort of push things a little bit. So we don't actually know which one will work here, right? It could be that U is 0, it could be that V is 0, but it can't be both, right? So all we know is that U plus V is greater than or equal to 1. You guys agree? Right? And that's basically the same thing as what you were saying, just like observing they actually end up being, like both cases actually are the same. Because you don't actually know what it is going to be, right? It is true that if it's B, then it has to be a 0, or it has to be at least 1 0. But when it's D, you don't actually know, right? It could still be, because R is allowed to be 0, right? Which means that D could also just have zeros in it, right? So it ends up just being this, right? But we're still fine, right? We can still, okay. Allow me to allow me to show you guys, just so you see that it's actually not that annoying, right? If we just pump down again, we again get ACE, right? And this is just going to be 0 to the 2p minus u, 1 to the 2p minus v, but 2 to the 2p, right? That this is going to be in L2. Of course, that's not going to be the case. That's still just an immediate contradiction, right? Just from the fact that u plus v is greater than or equal to 1, right? We're missing at least something here, whereas we haven't even touched the 2's, right? So, yeah, so you can like in your mind split and then realize, wait a second, there's actually no split here, right? It just works, right? And of course, case 3 is just going to be exactly symmetric, so I'm not even going to bother writing it down. Right? That's just when it is on the other side of the one, right? So that completes the proof, and we have our very first non-context-free language, right? Any questions about this? It's a little annoying, but it's really the same type of argument that we've seen before. Yes.
For formatting,
Mhm.
an exam, are we just, if we see clear symmetry, can we just say, can we just show the two different cases and say all the rest are symmetric to them?
Yeah, absolutely. Yeah, this is completely fine. Like when you're doing something like this and it's like exactly symmetric, this is a perfectly valid thing to say in a proof. Yeah, on the exams, in your homework, wherever stuff like that comes up. Yeah. Yeah, so case 1, this is case 1. Right? Case 1 is that BCD is entirely composed of 1s, right? And then case 2 was this. That means it's composed of some number of 0s and then maybe some 1s, right? At least 1 0 and maybe some 1s. Could be 0. And that's what we wrote down here, right? It's 0 to the t, 1 to the r. T is at least 1, but r could be 0, right? And then case 3 is just the opposite side, right? This is case 3. It's just like exactly symmetric, but where it's at least 1, 2, BCD has at least 1, 2, and 0 or more 1s. Does that make sense? Okay. Right? And then, yeah, the annoying thing, I'm just going to say it one more time, is that knowing that BCD equals 0 to the t, 1 to the r, what does that exactly tell us about BD? We actually have to be a little more expansive here and realize that all it means is that it has some number of 0s or 1s and at least one of them, right? Does that make sense to everyone? And then that allows it to go. If you think about it, actually all we really needed was case 2 and case 3, which is what one of you guys was saying earlier, right? That actually case 2 and case 3 already cover everything, right? We actually didn't really care about this. We only just cared about that t plus r is at least 1, right? Because anyway, if we're only concluding this, that could have just as well come from t plus r is at least 1, right? Yeah.
Every context-free language has a tree, right? Without like loss of any generality, can we assume that we're using the minimal tree?
Absolutely. So if when we were proving the context-free pumping lemma, that's what we did, right? We said like, suppose.
In this case, for example, are we allowed to assume that we're using the minimal tree as part of our assumption, or no?
Right. So what you're doing is you're like breaking the context-free pumping lemma abstraction, right? Like we don't need to do that because we're using the context-free pumping lemma, right? If you wanted to like reprove it from scratch, then sure, you could say, okay, let T be a minimal derivation tree for 0 to the 2p, 1 to the 2p, 2 to the 2p. And then you could try to get a direct contradiction from that. But that's like working harder than you need to.
I was just thinking that way you could just assume that, for example, BD already contains, like, one of them is guaranteed to contain, like, a 0, for example, or 0 to the t, 1 to the r case, and that way we wouldn't have to do the extra step. I'm not sure
Yeah, I'm not sure either. We can talk about it maybe in office hours or something like that. But yeah, question.
Yeah, why is it not possible for BCH to be all zeros and then just have like all the ones and twos be
That's case 2, right? BCD equals all zeros. Just means R equals 0. Yeah. Yeah. So again, you can simplify this in many ways. We could spend a lot of time on it. Yeah, question though.
For case 3, when you say symmetry, you're saying that BCD is equal to this time 1T is 2R?
Yeah, it would be BCD equals 1 to the R, 2 to the T, just because that's the same case, right? Because you know you have at least 1, 2, but you don't know if you have any 1s. Yeah, the way that you guys have set it up, that's what it would be. Yes.
Unlike homework and stuff, can we say that it has to happen within the first 0 to the P characters?
No, we actually did not prove that,
I mean,
right?
You could prove it, but like, you could probably prove that not too bad, right?
All right, I'll give you as a challenge problem. Prove something like that for me, and I'll give you a lot of extra credit.
Okay.
It's not that easy.
Okay.
Yeah. Yes.
We asked before, but wouldn't we also need to show symmetry for case 1 also if BCD is entirely contained in 0 to the TP or 2 to the TP?
So just what he suggested was that case 1 would that it only contains 1, only contains 1s. Now you're asking, did we need to do that? No, we didn't. But it was what you guys came up with, and you can just roll with it, right? Like, it is actually possible to simplify this even further. You really only need 2 cases. That it either straddles the 0, 1 boundary or the 1, 2 boundary. And it can just have, it can have U zeros and V ones such that U plus V is greater than or equal to 1. Like, that's all we actually needed, and that's all we actually used, right? So after the fact, we can see how to simplify it, but there's no need to. So like, I wouldn't get too worried or obsessed about that. Yeah.
For that approach, there are actually overlaps because
Sorry?
for the approach you just mentioned, the boundary ones, the purely 1 is actually in both cases, right?
Yeah.
Okay, cool.
That's right. Yeah. Again, we only need the cases to cover, right? Yeah, absolutely. All right. Again, let's not worry about any optimizations. Does the proof make sense? Anyone here still having any trouble with the proof as written right now? Right? There are ways to optimize it further. I'll give you guys that. But we don't care about that. Remember, this class, we don't care about optimizing things. We just want to know the truth. Is it true or is it not true? Right? Okay. Let's move on. Actually, before we move on, I want to point out something. We can now start drawing kind of a pretty picture, right? So we have a giant set of all languages. Right? And then we know there's a subset of regular languages. But we know, for example, that L1, 0 to the n, 1 to the n, is outside of the set of regular languages, right? But now we can draw a bigger circle, right? And we can call these context-free languages, CF. And we know it contains L1. But now we know there's something outside of that, right? We have L2, which is 0 to the n, 1 to the n, 2 to the n, right? And so we're kind of starting to build up this onion, right? These different layers of what different models of computation are capable of doing, right? And we have just proven for the first time some non-triviality, right? Is that a question? Yeah.
Are context-free grammars such grammars such that they encapsulate regulars, or is there a continuum language in between context and
It's a good question. So there certainly are even more limited forms of context-free grammars that actually only capture regular languages. I bet that you could come up with something. I don't know how natural it would be. That would be in between. Actually, if you look in the book, there are some examples, but I personally don't think they're very natural. So if you look at the chapter, we're not going to bother to cover that though, because as far as I'm concerned, we are just getting towards the very end of what we want to cover with regard to stack machines and context-free languages. Question? Okay. Maybe though, before we leave stacks and context-free grammars behind, do you want to do one more language? Should you prove one more language is not context-free? Yeah, let's do it. All right. Someone, please suggest to me a language that they think is not context-free. And let's try to prove it. Oh, actually, sorry. I guess that's not that useful. Let me just erase this. You have a suggestion?
Just repeat the same pattern 3 times.
Okay. Like 0 to the n, 1 to the n, 2 to the n, 3 to the n?
No, I
Oh.
mean XXX.
Oh, sorry. Okay, now I understand what you're saying. Okay. Got it. I like that. I'm going to take your suggestion, which is definitely worth a token, and actually let's make it even simpler. So what she's suggesting, right, is the language that looks like this. X, 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 such that X is in sigma star, right? Repeating the same thing 3 times. But to keep things, G-rated around here, let's actually just call it XX, okay? How about that? What if we just repeat the same thing twice? What do you think? Yeah.
Isn't that finite?
What's that?
Isn't that finite?
No. X is in sigma star.
Sorry, sigma star. Sorry, never mind.
Yeah. Yeah. Right? And the reason why I suggest something simpler is that, again, think about stacks, right? Like, if I tried to verify XX, I can push X to the stack, but now everything is in reverse order, right? How am I going to check, right? So at least intuitively, just XX should be hard, right, for us to do with a stack machine. So let's try to prove it. So again, claim L, okay, let's just call it L, is not context-free. So of course, we suppose not. So we're saying SL is context-free, which means by the context-free pumping lemma, there exists some pumping length P. And now we get to the first non-trivial. Maybe I'll just not use X. Let's call it W. So what do you guys think? What should we let W be? What should our construction be if we want to find an element of L that we can apply the pumping lemma to and get a contradiction? Any ideas? Yeah. Nice. All right. So a similar trick, right, to what worked for us over there. We are repeating something non-trivial twice. Let's go for it. Let's try that. Okay, excellent. Definitely worth a token, right? So we have in our hands our W. Again, of course, it's longer than P. So by the context-free pumping lemma, there exists A, B, C, D, E, such that W equals A, B, C, D, E, right? And as usual, we have that BD is at least 1, and BCD is at most P, right? What do you guys suggest? for a case analysis? Yes. Okay, just tell me where should BCD be? Like what's yeah. Good. Okay, that's case one.
Or you could be within just the second half, or you could be like somewhere in the middle.
Or in the middle. Okay, good. So these can be our three cases, right? Okay, so case one is that BCD is equal to, let's just use this R and T, right? So, oh, I guess that's, anyway, but yeah, it's like this 0 and 1, right? And again, all we know is that it contains at least something here, right? Okay, excellent. Thank you for getting us started. Definitely worth a token. How should we get to a contradiction in this case? And again, this is like, I don't know, maybe say on the left of W, right? In the back. Pump down, okay. So yeah, so what would it look like? 0 to the, we know it was over here that we did the pumping down, right? Oh, actually, yeah, sorry, hold on. We have to do one more like little annoying thing. So just remember how we had like BCD and then that implied something about BD. So let's just do that again. So if BCD equals 0 to the R, 1 to the T, this implies BD equals what? What do you want to do here? Say here. With the V such that? Yeah, right? Again, all we're saying is it has to contain at least something, right? Okay, and now we'll pump down. And then what does that yield? Yeah. Yep, right? Because we know wherever we did the pumping down, it happened in the beginning. And again, this is saying that this is in L, but that's obviously a contradiction, right? Clearly, this is not the same thing repeated twice. Excellent. Thank you. Yeah, definitely worth a token. And observe that case 2 is exactly symmetric, right? So this is, again, just symmetric. So the only case we have left is where BCD straddles the very center of this, right? So the end of the first X and the beginning of the second X, right? So does anyone want to bring us home? Yeah? 1 to the R, 0 to the T, such that, right? And that implies BD. Okay. Pump down again. Zero to the P, 1 to the P minus U. 1 to the P, right? And again, it's just by inspection. This cannot be in the language, right? Because either V is at least 1, in which case this 0 to the P and this 0 to the P minus V don't match up, or U is at least 1, in which case this 1 to the P minus U and 1 to the P don't match up, right? So we get contradictions in each case, and that finishes the proof, right? Excellent, thank you. Definitely worth a token. Again, any questions about this? Yes? Yeah, so case 3, right, is this right in the middle, right? So this is where we are, we might have some of the end of the first string and some of the beginning of the second string, right? So that means it'll be 1 to the r, 0 to the t, right? Because it's like right at the end of the first string, right at the beginning of the second string. And again, all we know is that r plus t is at least 1, because we don't know which one we have exactly, right? Again, bd is a substring of this, which is non-empty. So we'll just write that as 1 to the u, 0 to the v. U plus v is greater than or equal to 1. Does that make sense so far? Right? And now we just pump down. ACE will be 0 to the p, 1 to the p minus u, because we're pumping down this 1 to the u. That'll come out of the first half, right? Then we're also pumping down the 0 to the v, which will come out of the beginning half of the second string. So that'll be 0 to the p minus v, 1 to the p. And again, this just can't be in our language XX, because something is not the same, right? Either the number of zeros is not the same or the number of ones is not the same, right? And that gives us our contradiction, right? All right. So yeah, now we have another guy that's outside of the context-free languages, right? This is this XX guy, right? So yeah, so that like lets us understand that even though we gave ourselves this unbounded memory in the form of a stack, because of the stack nature of it, right, it actually has some really significant limitations, right? And again, on the one hand, we should feel good about ourselves. You guys have figured out how to develop the theory. You've figured out how to prove that things are not context-free. That's cool. But it's still a little sad, right? We're saying the whole universe as a computer cannot tell if a string is the same string repeated twice, right? Like, that's our great answer to, like, what is the limitation of the computational power of the universe? And it just doesn't feel right, right? It doesn't feel like it's the right, like, great answer. And after all, how much evidence do we really have that the universe uses a stack as its memory device? Like, not very much, right? So there's definitely something missing here, right? And that brings us to, like, we're just going to start now, like, the final chapter, okay? And I shouldn't have said that. Sorry. Starting the next chapter. All right, next chapter. All right, so we know we have to go back to our notion of computation, right? And mess with it again, right? We're not happy with stack machines, right? We're happy with unbounded memory. That was a really good idea. But how should our machine have access to that unbounded memory? You know, we actually had a lot of suggestions that you guys came up with. It's basically my fault, but I said, hey, let's think about stacks for a while, right? Because that was one of your suggestions. And that took us down this road, which is very interesting, very cool, lots of interesting connections, but still finally unsatisfying, right? So if we go back to that, like, fundamental question of, like, how should our machine have access to the unbounded memory that it has? Does anyone want to remind me, what are some of the other ideas that you guys had? Like, how else could we give access to our machine? How else could we give our machine access to the memory that's unbounded that might get around some of these annoying limitations, right, that we see? Yeah. Arbitrary access. So what does that mean, though? Like, what does that look like? So again, we want to think about it as like there's like a DFA, some like simple dude that we've worked with before, right? And now it has access to something, right? And the initial idea was a stack, which is very nice. Pop, push, pop. We knew exactly what to do with it. What does arbitrary access mean? Like, what would the transitions look like? What does that mean? Okay, just move up and down. So maybe instead of arbitrary access, what you're saying is move up and down access. Right? I mean, it's like the smallest possible change, right, to our current model is what you're suggesting. Extremely natural. The only difference now is that instead of popping, you can just say, hey, just go down, right? And whatever was already in our memory stays there. It's just that like our current pointer, right? Our current pointer into memory goes down. So maybe we were up here at first. This is some A. And now we say go down. And now the pointer, points here, but the A is still there, right? Seems so reasonable, right? Question or comment? Yeah.
So are we talking about the DFA or about how many we can run? Are we allowed to use multiple stacks or multiple arbitrary DFAs?
Well, what she's suggesting is the simplest thing, where we still only have one stack, right? Or one like memory, we should call it, right? This is still like our memory. It's really not a stack anymore, right? All she's saying is now there's going to be like, it's a memory plus a pointer. Right? That's what she's suggesting. Like we have memory and we have a pointer into memory, and we can move that pointer up and down. Right? Does that make sense? I see lots of questions or suggestions in the. So maybe first questions. Yes.
Yeah, so how does the insert work here? Do we still only insert like the top, or can you like do like where the pointer is that we add stuff? How does it work?
That's a good point, right? And you kind of gave a good answer, right? So maybe what we should do is, what you can do is you can read, of course, at the pointer. That's what she was already saying, right? Read at pointer. Let me call it PTR. And what you said is like we should also be able to change at the pointer, right? So and change at the pointer, right? So we can modify memory wherever we're currently pointing, right? That seems extremely natural. Totally worth a token also, right? For making it happen. So yeah, let's do it that way, right? We can move the pointer up and down. It's unbounded. We can keep going, right? But we can read at the pointer and we can change at the pointer, right, into memory. Questions or comments or suggestions? Yeah?
I feel like now it's better to go if our memory is empty, right? So we can just keep popping. Is there a way to do it with this sort of
Yeah, I like that question. So I think what you're basically asking is what's going on at the beginning, right? So like right at the beginning, maybe the pointer is pointing here, right? But what is there? Right? Nothingness, right? So let's go with that. Let's say there's a special symbol called nothing. Okay? So let's say there is a special nothing symbol, which we'll write that way. It's like a blank. And like the memory just starts out blank everywhere. Forever, infinitely. Right? Good? Worth a token? Excellent. All right. That clarified that. Which is like how the memory is initialized. Special nothing symbol is how memory is initialized. Yes.
Yeah, this isn't really like a suggestion, but I was thinking about the possibility that this allows us to do, and I was thinking how like now you're able to read your input instead of consuming them,
Yeah.
and thus that'll probably like solve a lot of the problems that we have with context-free grammar.
That's a great idea, right? What he's saying is that we can immediately in the beginning just like copy our input into the memory. Then we can just like go to the beginning of it, right? So, and we could still like as a general rule, we could like put a funny symbol at the beginning, right? Just to like make sure that you know we know where the left, where the right, where the bottom of our memory is, right? But I like that idea too, right? What you're saying is that now sorry, give me a second. Now, without loss of generality, assume input. Sorry. Assume that the input is like preloaded. Onto memory. Right? Why not? Let's just always do that. We preload it onto memory, maybe with the funny symbol at the beginning, right? And just like move the stack all the way back, right? And now we don't have to worry about like terminating at the end of the input. Like our machine can decide when it wants to terminate based on whatever it decides, right? Excellent. Totally worth a token. Yeah. Yeah.
Does this mean that like we can't pop anything anymore because we have like a nothing symbol?
Yeah, we don't need to, right? Like we already made that change here, right? Instead of like pushing and popping, we just have a pointer, we read at the pointer, and we change at the pointer, right?
So like a nothing symbol means we pop.
But now, like we could, for example, let's say what we did was we put a funny symbol and then 0, 1, 1, 0, right? And let's say we move the pointer here. We could overwrite this with an empty symbol, right? A blank symbol. And that's not a pop or a push or anything. It's just its own thing, right? In the middle of the memory, we can just like erase stuff if we felt like it, right? Does that answer your question?
Yeah.
Yeah. Okay. Yeah.
I'm curious, like, what do we mean by generality there without loss of generality? Because I can imagine that maybe there's a program or like, you know, a setup that wanted to use both directions, but now there's like a programming the way where it would have wanted to make use of that these days.
Right. Okay. You're raising a good point, which is that I said without loss of generality, right? So I'm saying like any program might as well do this. And what I've shown so far is that it can do it, right? But what you're asking is like, wait, why is that with loss of generality? Like, what if you want to do something more clever, right? And this is like preventing you, right? It's a very interesting question, right? So does anyone see? Why would it be without loss of generality? So like, again, what I'm saying is that you can actually just, let's just say the input was 0, 1, let's say 0, 1, right? And like now it has blanks everywhere else, right? So I'm actually claiming that this is without loss generality. I can just start with the input loaded and it really doesn't matter. He's objecting, saying like, I don't know, I don't see the equivalence, right? Does anyone see? Like, why is that okay? Like, what if your actual algorithm, like your actual computer, really wanted everything to just be blank at the beginning, right? Like, what should our machine do instead, right? That's what you're asking. Is that correct? Yeah. Okay. I see some hands in the air and like a partial hand kind of in the air. Do you want to try?
You can just like shift your pointer up until you reach the empty.
Yeah. Right. The idea is that we anyway have, let's say, a funny symbol that tells us where our input starts. we could just put another funny symbol, let's say, at the end. What?
Carrot.
Caret, thank you. There we go. Okay. That looks, okay, sorry, that does not look good. I need a better funny symbol.
Smiley face.
Smiley face, yes, that I like, right? So I put a smiley face here, right? And if I want my machine to like work here, I can just move the pointer up until it's pointing right past the smiley face, right? And it can do whatever it wanted to there, right? And if it ever wanted to read the input again, it could just go back down and find the input, right? This is very interesting though, right? Like the flexibility, and thank you, that's definitely worth the token, right? And like the flexibility that just having memory and a pointer is giving us is already like a lot more than what we were used to, right? Does it, also, are you satisfied? Do you feel like that's a reason? Not satisfied, or you are?
I'm not.
You're not. Okay, please explain your objection.
I think my objection is like, I grant this gave us like more space to work with, and we started at a new fresh state. So
Yeah.
but I think like if we had a purpose for using those exact same spots like, to do work, that it's a problem that things have been written down.
I'm sorry. Can you say it one more time? What the objection is?
So this was like the first step of like writing things down, but if like during the actual like real work, besides just this first step of writing things down, like wanted to use those exact spots in memory that are currently occupied by nothing symbols. Like I had a reason for going up an arbitrary amount or going down an arbitrary amount throughout an execution of my machine.
Right.
Then like I figured it might be a problem that those symbols aren't using the spots I might otherwise be, or like I might misread them when I like.
Okay, actually, that's a really interesting objection. Okay, so what he's saying, and let me make some more room for myself because I really like this discussion. So his objection is, wait a second, you know, what if my computer really wanted to make use of like these specific spots in memory, right? Like I have a dollar sign here, I have a 0, I have a 1 here, and I have a smiley face, right? And you're telling me, hey, go use that part of memory. But what if your machine really wanted to use this part of memory, right? What do you guys think? Is that a reasonable objection? Or do you see like a nice way to answer it? Yeah, what do you think?
I think you could just copy that right above it, and it would practically do the same thing.
Yeah, right? The point is, this is like a semi-infinite memory, right? So whenever your machine wanted to use like position I in like an array, just tell it to use I plus 1, 2, 3, 4, right? Just tell it to use I plus 4.
I think the trick is that I might have a reason for wanting to use both directions. Because like I feel like by inserting.
Sorry, what do you mean by both directions?
Perhaps I need to recognize the language, and the way I want to be doing it is by counting up arbitrarily, but also counting down into the negatives arbitrarily, or something like that.
Well, even our stack didn't let you go below 0, right? So even otherwise, what we've been thinking of, what you suggested and what we've been developing, doesn't let you go like below the bottom of the memory. Okay, then no objections. All right, good. But this is actually a really nice point, right? This point, which is definitely worth a token, right? Which is like, once we have this pointer, we can actually kind of keep going back and forth, right? Like we have this ability to go back and forth, and like this could be like our workspace, right? And like here's where our input is, and we can kind of keep going back and forth. That's very interesting, right? So okay, I see a lot of like thoughts and suggestions. So let me just take them one at a time because I haven't gone there. Let me go with you first.
I have like two questions. One, like, didn't we arbitrarily decide to add the character to indicate the start of everything? So like, if we just left it as unbounded anyway, like, isn't that not a problem really? Like in terms of have it going infinitely upwards, and it's random, like it's essentially a random access.
Well, it's not exactly a random access memory, right? I was actually thinking that's what she might be suggesting originally. But remember, in a random access memory, in a RAM memory, you actually have like an address buffer, right? And then you have separately like the actual memory, right? And like where you point to in your, like you first figure out the address. The address points now to someplace in memory, and then you retrieve it, right? So that is actually a different model. This is a much simpler model. There's only one pointer in this, right? There's just like the one place that our DFA is pointing, and the DFA can tell the pointer, hey, go up or go down, right? Do you agree with that? That's the model that we have right now.
Yeah, but then wouldn't you just be able to like set a character and just say like use that as an offset? That's your address buffer essentially, because then you just know that that's 0 or whatever, and then you just go.
Okay, interesting. What he's saying is he thinks maybe these are equivalent. I like that question. Definitely worth a token. I would say we haven't really defined this fully yet. But once we are able to define it fully, right, it's a great question, right? And let me actually just pause for a moment to say, like, it's a really great question, okay? And one reason I would say it's a really great question is that that is basically what this is, right? Like the von Neumann architecture, right? The architecture that like all of our computers are built on is the random access architecture, right? Where you can actually just write down addresses into memory and load and store and do whatever you want, right? So like, it's more complicated, which is why I still like her suggestion better, right? And I think we should focus on that one for a while. But like, if we go all the way to RAM, then we've actually more or less gone all the way to this, right? So that would be pretty impressive, right, if we could. So it's a great question. Is it actually equivalent? Is this model that we're starting to develop right now equivalent to the random access model, right? That's what you're kind of underlying your question. I saw some other hands. Give me 1 second. Yeah.
So in the move up and down axis, you know, we read and we change wherever the pointer is pointing.
Yeah.
Don't we also need some sort of a search feature to tell, hey, pointer, go to this part of the memory?
Yeah, great question, right? So he's kind of objecting, in some sense, to what you were saying, right? Which is, a RAM would let you just be like, hey, go forward, you know, some number, right? Like it would let you do like relative addressing, right? Whereas this kind of pathetic model that we're building right now just says, hey, go up 1 step, or like go down 1 step, right? So yeah, it's a good question. It's a good question. It's not obvious. That's why I put a question mark, right? Like, is it equivalent? Unclear, right? This model seems a lot more limited, and crucially, it's very local, right? Like the model of computation that we're developing right now that she suggested is very local, you know? Like I can only look at this one little part of memory, decide what to do, and go either down or up, right? That's it. That's all I'm allowed to do. Whereas like a RAM model is not local at all. I can, in one instruction, change this location of memory, and in another instruction, change some piece of memory that's like extremely far away, right? So it's, it's a very interesting question. You know, is non-local equivalent to local? Like, is that, like, what's going on there, right? That's the question that you're wondering about and not so sure, right? Very reasonable. Yes?
So for the memory thing, I'm thinking, because we can define address with movements of pointers, right? So, for instance, we start at a random place in an infinite universe.
Yeah.
And we don't know where our starting address is. But whatever data we have stored, we have to be able to reach it somehow, and that has to be finite. So you can get to there through a finite number of states.
Right.
So any address you actually use, you can actually just get to there with our architecture, right?
With some finite number of steps. That's true.
Yeah.
That is very true, right?
Yeah, so like with RAM,
Mm-hmm.
if you want to access a memory, say over there,
Yeah.
or down here, and you can just go up.
Step by step,
Yeah.
right?
Right.
Yeah, like that seems reasonable, right? We haven't really bothered to define this completely yet. In particular, what exactly is the address buffer? Like, we haven't actually figured that out yet, right? So we're gonna have to figure that out, right? Also, you know, at least in this computer, right? When I store my addresses, I store them in binary, right? At least what you were suggesting initially would work if you stored your addresses in unary, because then you could just like count them out, right? And like, that's very interesting, right? So in order for that to work, we would have to be able to do binary arithmetic. We would have to do like at least counters. We have to do like -1, right? So that's an interesting question. Another interesting question we can put out here. You know, this new model, can it do binary arithmetic? Good question, right? Yes.
Just a thought, but can't we simulate multiple stacks using this? And just have like a symbol that differentiates where the stack ends?
Okay, excellent. Hold on. Let me find another place to erase. So another suggestion that has come up several times with different students over the last few days, mostly in office hours, has been the suggestion of multiple stacks, right? And maybe I can modify what you're saying even slightly more. What about just like multiple of these things? Like whatever they are, right? These multiple memories. What about like multiple memories, each with its own pointer. Let's say there's a pointer here and this one has like a pointer here, right? What if we had multiple of them, right? Is that equivalent? To that, right? You're suggesting that you think it should be, right? That there should be a way of like maybe just concatenating them with like some special symbol in between, right? Onto our one memory, because after all, our memory is semi-infinite, right? Like it's unbounded, right? It's a very nice question, right? Excellent, definitely worth a token. Good. Yes.
I feel like if you're able to prove that those two are equivalent, then we can also say the same thing for infinite amount of stacks.
Infinite amount of stacks. Okay, so I have a problem with that. Okay, and the problem I have with that.
I think I know what you mean, because if you could go like up and down, but once you go up.
No, I had a much more basic objection, right? So like when we think about this machine, like our basic machine that we're building up, right? Like how do you describe it? It basically is described the same way that we described our stack machine. It's just that now instead of saying push and pop, you say change this and go up, change this and go down, right? Like you can just describe what you want it to do very succinctly and definitely finitely, right? The machines here are finite. Even when you have two of them, it's going to be a little more annoying, but you can say, okay, I'm going to transition from state Q to Q prime, and I want you to change this on your first memory and go up. I want to change this on your second memory and go down, right? But it's still finite. It's more complicated, but it's still finite, right? But if you have infinitely many of them, then you have to like tell infinitely many instructions, right? So that's the problem that I have. Like remember, it is an essential thing throughout this whole class that all of our notions of computation have to be finite. Like the computer itself should fit in a finite amount of memory.
But then I feel like it goes back to the point where you pointed out that you could do the iPhone 4 where because the stack is semi-infinite. That kind of like I feel like inherently tells you that you could also do an infinite number of stacks.
Well, again, the memory is like unbounded, right? Eventually, the machine can go like further and further, like up the memory, right? But still, when it comes to like describing an instruction that our computer is carrying out, each instruction is finite, right? If we had infinitely many memories, how does the computer even say what it wants to do, right?
I thought about you reminded me of like countable and uncountable.
Yeah, all right. Those things will be coming up.
Yeah.
Those things will be coming up. All right. But yeah, I'm not saying it's impossible. You could imagine like a two-dimensional array that are infinite in two ways, right? And maybe you have 2 pointers. Like you have a pointer that tells you which memory you want to access, and then like a pointer that remembers where we were in that last, right? So that's certainly possible. That would be finite, but like another kind of memory. So absolutely, guys, like this is not the only model. This is just the simplest evolution, right? Like we're taking our stack model and evolving it in essentially an almost like extremely tiny way, right? We're just like saying, hey, instead of popping, I can just go down and then go up, right? All right. I see there are still more hands in the air, but I think we're essentially out of time, so I'm happy to just continue in office hours. I'll see you guys at the midterm exam, and then we'll continue in 1 week. Thanks. Hey.
I just want to make sure I'm not wrong about something.